right, so that's one of the stuff that you were supposed to watch over the weekend. Those are from the more advanced electromagnetic wave theory lectures. So Newton was wrong. Newton thought that the waves could only transfer energy. That's not true. They can also transfer momentum. Because they can transfer momentum, they also generate radiation pressure. All right, so Huygens is the winner in this argument. All right, Huygens is the winner in the argument because the argument is settled by Young's double slit experiment.
In the early 1570s.
Go ahead.
So they did tests and found that some particles behave as waves as well, right?
Okay, all that. That's modern physics.
Christian Huygens.
But
I want to keep things in the classical physics realm right now. Just hold on to this.
Formulated the principle of light waves.
Say again?
Why'd we go over it already?
Because I'm weird. Just hold on to it.
Stating that every point on a wavefront is a source of new waves. And in 1801, despite the prominence of Newton's rival corpuscular theory, another Englishman, Thomas Young, proved beyond a shadow of a doubt that light is a wave. He accomplished that by proving that light has the wave property called interference. Wave interference can be seen to be constructive or destructive. If the waves, as they travel, encounter each other in step, they can reinforce each other, create a stronger wave, and produce what's known as constructive interference. But when they're out of step, waves can cancel each other completely. In other words, destructive interference. As Thomas Young suspected, all waves in all media behave in this fashion. And to prove that light is a wave, he merely had to illustrate that light exhibits interference, the behavior common to all waves. Here's the principle. Light from a single source enters two slits, which are side by side and not much farther apart than the wavelength of the light itself. After passing through the slits, the light shows up as a distinctive pattern on the screen. When a single plane wave encounters two slits, each slit becomes the source of spreading wavefronts. And because both new waves originate from the same plane wave, their oscillations are synchronized. The result is a stable pattern of up and down ripples, alternating with directions along which the waves cancel one another. This produces a pattern of bright fringes of constructive interference on the screen, separated by dark fringes of destructive interference. And that was it, a series of alternating fringes to prove that light is a wave. It was a conclusive demonstration, and ever since, physicists have had to explain the behavior of light in terms of the properties of waves.
All right, so we got the dark and bright fringes. Okay, so what does that prove? What's causing the bright fringes?
Constructive
interference. Give yourself 2 points. And the dark fringes?
Destructive.
That's it. All right, only waves can interfere constructively or destructively. Hence the proof that the light is a wave. That's it. All right, so when they are in phase, it's going to give you a bright fringe, constructive interference. Another constructive interference. And when they're out of phase, which means that the waves are interfering destructively, the amplitudes will cancel, so you end up getting a dark fringe. Okay, so we didn't discuss that, but just want to see where you guys are at.
B?
Okay, Matthew, why did you say B?
Yeah, I said B.
As in boy?
Yeah, because when they entered the slit, it looked like B.
Okay, very
of course.
I'm gonna give you 10 points for that one. Yeah, guys, every single point in this gap is gonna act like every point on a wave behaves as a source of a new wave. All right, at the slit. So, or else you can't do this sort of stuff. All right, mathematically. All right, so the interference is a property of
D.
All waves. Right, so those of you guys who pick D, give yourself 5 points for that one. So what do we know? Huygens said the light is composed of waves. Newton said particles. Young's double slit experiment proves decisively that the light is a wave. So now going back to what Ian was talking about. Okay, so when you repeat the experiment with particles, you end up getting a wave pattern. So what does it mean? What that means is, despite the fact that we're working with particles, they also have a wave nature. Those are known as matter waves. There's a rich history behind it. Those matter waves later on became probability waves. That forms the basis of quantum theory. Particles are particles, but they're waves, and they got waves associated with their motions, which are known as matter waves. So that's from modern physics. All right, so far, what do we know about light? According to the Classical physics, light is a wave. It's not a particle.
But if
Okay, so yeah, go ahead.
the proof that light is a wave is how it behaves on this double slit experiment, and an electron behaves in the same way. Does that not remove that as proof of a wave?
Okay, Ian. I love your question. This is the last couple of lectures. The last couple of lectures usually these are cities for modern physics. Okay, so these are the questions we deal with in modern physics. Speaking of electrons, okay, here's the question. Number one, they have a measurable mass. They have a measurable charge. So if they have a measurable mass and if they have a measurable charge, you can make the argument that these are particles, right?
Yeah.
Okay, but then again, you can also make the argument that they can also be waves somehow. All right, so there's a little bit of fuzziness there that makes modern physics really, really interesting. So for the sake of argument, from a classical physics perspective, assume that they are particles and somehow they have a wave nature. So the question is, what's waving and what's interfering? What's causing the interference pattern when we repeat the experiment using particles like electrons or atoms or molecules? All right, so a lot of this stuff that I introduced was just a tease for modern physics, because normally I would, right after this, I would be teaching modern physics. And most of you guys will take modern physics somewhere else, but that's fine. So, modern physics is stranger than fiction. So, you know, I'm going to give you 10 points for the question. So that's a good question. All right, so for the sake of argument, just stick with the experimental results. So the experimental results so far, according to classical physics, light is a wave. According to modern physics, it's going to have a dual nature, but that's for modern physics. All right, so this is just for the mathematical setup. Okay, okay, let me go over the terminology here. So D is going to represent this slit separation. So we have double slits, S1 and S2. S1 is either the first slit or the first source. S2 is the second one, second slit or the second source. All right, there's going to be an interference taking place on the screen. All right, so we have two nearly parallel rays that you're looking at. So the distance, the screen is further apart. These rays are not exactly parallel, but from a distance, they're going to look parallel, and they will converge to a point. That's what it's. All right, so we're looking at the lights at the source of double slits. All right, so this is the path that the light on top is going to take. L1 is going to be the first link. This is the path that the second one is going to take. L2 is the second path. All right. And then we can make a small triangle here, right angle triangle. Notice that this bottom is going to be 90 degrees. Delta L is going to represent the path length difference. And then you have this angle over here. All right, so this angle that you're looking at will be the same as this angle that you're looking at here. On the screen, we will have a fringe pattern. Notice that right at the center, it's going to be a bright fringe. So you have the first constructive interference pattern, the second one, the third one, or whatnot. It's just going to, so this is known as the first order constructive interference, the 0th order in the middle, the first order, the second order, and so forth. Okay, so that's the general setup. The math is going to come out of this. All right, so it's the same setup that I just discussed. So let's just come up with the mathematical explanation for it. All right. Okay, so you will find the derivation here. Okay, so interference of light, chapter number 37. We just had a discussion regarding that. So that's the Young's double slit experiment. So I'm just going to take you through the derivation. All right, so it's the same derivation as what's in the handout. All right, so we got two slits, S1 and S2. So these are going to be our sources. All right, so we got two waves coming out of two rays, more like coming out of the parallel slits. They're almost parallel to each other. This one is going to have a slightly larger angle than this one, but the angles are going to be relatively small. All right, so D is going to be the slit separation, distance between the sources. Okay, so we will form a small right angle triangle there. Okay, so the 90 degrees is going to be right there. The first length, the second length, delta L is going to represent the length difference or the path difference.
But so
right. Okay, go ahead, Ian.
delta L is the length of the small piece at the bottom, or between the two paths?
Okay, this delta L is the path difference between the two paths that you're looking at.
So
okay, so yeah, go ahead.
The length between them?
Okay, L2 is going to be slightly larger than L1 at the point of interference on the screen.
Okay, I got you.
Okay, is that making sense? All right, give yourself 5 points for the question. You guys just stop me every time you have a question. So we got all the time in the world. All right, this is a new method that I'm trying. I think this is so much faster than me just writing and talking. All right, so now drawing the triangle. So these the separation distance delta L is the path difference in the lengths. All right, theta is the same. All right, so we're looking for a constructive interference pattern. All right, now for the constructive interference that happen, the path difference should be in the order of the wavelength between two waves. If that's the case, it's going to end up giving you a constructive interference pattern. Okay, so the thing I don't like about that explanation is it's something that needs to be described visually. All right, so let's try to come up with a visual explanation for it. I didn't get a chance to do a recording on it, so I have an idea. I'm just going to play with it. And hopefully it will make sense out of it. All right, this is the sort of stuff would work well if using a overhead projector usually. All right, so let's talk about wave interference. All right, this concept that I'm about to describe is very crucial to your understanding of how the waves interfere from a mathematical perspective. All right. All right, so this thing is moving from left to right, so it's going to have a speed. All right, here's a single wavelength. All right, so this will be a single wavelength. All right, so if you represent this in terms of a length, this is a wavelength. If you represent this in terms of an angle, this is going to be 2 pi. It's going to be 2 pi radians. All right, I'm going to change the notation a little bit because we will use similar notations. All right, I can represent this in terms of, let me change the color. I'm going to use this symbol denoting path length. All right, so which is going to be expressed in terms of wavelengths. And I'm going to use this notation in terms of, let's just make this like that. They're not equal, but they're related. All right, let's make it like that. This is going to be our phase angle notation. Okay, so let's make this phase angle. I'll explain what it is shortly. All right, so that's the notation we will use for that one. And we will also express the same idea in terms of the path length. All right, so these are the notations we will get to use. Okay, so what do they mean? All right, I'm going to come up with a visual. Yeah, I wonder if I should grab the entire thing. All right. Okay, so we can play with it. Okay, cool. Okay, guys, these two waves. Okay, so when you add them up, what do you get? Do you end up getting a constructive or destructive interference pattern?
Constructive.
It's going to be a constructive interference pattern. All right, so visually, here's what I'm going to do. Forget that. What do we got? We add them together on top of each other. All right, evidently these are not quite in phase. Oh, this is beautiful. Okay, notice that when they're on top of each other, the phase difference is 0, or phase difference is just a single wavelength. If that's the case, you end up getting a constructive interference pattern. That's what it means. All right, so when you add them up, what do we end up getting? So what's going to happen when you add them up? This thing is going to be a constructive interference pattern. When these two added together, this is what you end up getting. This is constructive. So if that's the case, what is the phase difference between these two? Okay, I'm going to show you mathematically, but before we do that, there's no phase difference. They're right on top of each other. Okay, so that's what it means. All right, so I'm going to change the concept a little bit right now. Okay, so I'm going to grab this, just pull it to the side. All right, I'm going to move this to the side. Okay, what do you think you're going to get at this point? It's going to be a destructive interference pattern, right? They will cancel. All right, so I'm going to place them right on top of each other. What happens is they will cancel. So what is the phase difference now between these 2 points? How much did I move it sideways? Notice that I end up moving it by half a wavelength, or I end up moving it by pi over 2 in order to cause a destructive interference pattern. Is that making sense? So the phase difference means that these are not on top of each other. One of them is displaced with respect to the other one just slightly. That's what it means. All right.
Wouldn't pi over 2 be a quarter of a wavelength?
No, you're right. It should be 180 degrees, so it's going to be displaced by pi. Give yourself 5 points for noticing that I didn't say it right. Very good. Okay, yeah, that's exactly right. Okay, so let's do this again. So I'm going to change the notation just a little bit. All right, so this is 1, this is 1, this is 2, this is 2. All right, and then I'm going to get them on top of each other one more time. All right, so, Okay, now you can see the phase difference easily. All right, so when you're talking about the phase difference, so what is the difference between this and that, if that's the case? All right, so if we're talking about the phase difference, we're talking about phase difference in terms of this. All right, notice that phase difference here is going to be pi, right? So that's going to give you a destructive interference. Now you can take a look at the path difference. All right, in this case, the path difference is going to be, it's going to be half a wavelength for the destructive interference.